So if you're relying on large language models for, the really complex stuff, you probably know the classic LLM
Oh,
journey.
yeah. The escalation path.
Exactly. You start with the smaller, faster models, and when they fail on the tricky parts, you assume, okay, it's an intelligence problem.
Right. It's just not powerful
So
enough.
you scale up, you go to the next tier, and pretty soon you find yourself using the biggest, most computationally intense model there is. The one that's supposed to handle anything.
It's the default move, isn't it?
Yeah.
We just equate complexity with raw computational muscle.
Mm.
We think if the problem is hard, the biggest model has to be the answer.
And that mindset is exactly what we're digging into today. The crucial pivot here is when you realize you can be using that absolute top tier model and still fail.
Dramatically.
Yes, when you try to do it all with a single prompt, you hit this, I don't know, this functional complexity wall. And it's so frustrating because it feels like the model should get it, but it just keeps giving you junk.
And that feeling, that's the signal. It's the sign to stop chasing a bigger model and start building a better architecture.
So not a bigger brain, but a better plan.
Exactly. The solution isn't more brain power, it's changing the whole structure. We start making one massive monolithic LOM call and start building what we call an agentic workflow.
Okay, an agentic workflow.
This decomposition, it shifts the focus entirely. You're moving away from generalized intelligence and towards functional specialization.
Okay, let's unpack this. Our mission for this deep dive is to show you exactly how this works. We're looking at a real-world scenario, a seemingly simple problem that completely stumped the biggest LLMs when they tried to solve it in one go. We're going to break it all down, step by step. The initial challenge we're looking at, it came from an internal audit. A company needed to check up on customer grocery orders where, employees had trouble finding some of the items. It was really about accountability.
And like all real-world data, the input was messy. You basically had two main pieces of information that needed to be cross-referenced.
The first one, let's just call it the missing items list, or column B. This was just a clean list of everything the customer wanted but didn't get in their final order.
Simple enough. You ordered cheese, ham, and milk, but you only got milk.
Right. So cheese and ham go on this list.
And the second input was the employee notes, column A. And this was just a stream of unstructured text, sometimes short, sometimes long, where the employee was supposed to explain why they couldn't find an item.
So the core task was this. Look at every single item in column B, the missing items, and make sure there was a corresponding, and this is the important part, a valid explanation for it over in column A.
A valid one, yes.
So if something was missing but the notes didn't have a good reason, the system had to flag it. And the output had to be in a very specific format, just a simple text file line like cheese, no explanation.
So the first instinct, of course, was to just bundle it all up.
The classic single prompt.
Yep. Take all the raw data, the missing items list, the huge block of notes, the output format, and just feed it all into the biggest LLM you can find. The prompt was basically, hey, cross-reference B with A, figure out if the reasons are valid, and then only output the failures in this exact format.
And what happened?
It failed.
Why? I mean, it seems like something a huge model should be able to do.
Well, it could handle the really simple cases. If ham was missing and the note clearly said stocked out, fine, it passed. But it just fell apart on the edge cases.
The edge cases.
Always the edge cases. The real difficulty wasn't just finding the note. It was that step of performing judgment. The example that really broke the whole thing was the infamous meh.
Meh.
Yeah. If the employee note for why they couldn't get the cheese was just the word meh, or, something like couldn't see it, or I forgot. I mean, technically those are explanations.
But they're definitely not valid reasons. Not for a professional shopper, anyway.
Exactly. And so the single giant LLM, which was trying to do extraction and cross-referencing and semantic judgment and output formatting all at the same time, it just couldn't reliably tell the difference between a good reason like temporarily out of stock and a useless one like meh.
So all those competing jobs inside one prompt just broke it.
It overwhelmed its ability to handle multi-layered logic. It's a classic case of what you could call prompt contamination.
Prompt contamination, I like that.
You're asking it to run in 4 different functional modes at once. And when it hits that ambiguity, that, the model gets stuck in a logic bottleneck, it might say prioritize the easy part, like the output formatting, over the really hard part, which is the judgment call.
And you end up with garbage output.
Inaccurate classification.
Yeah.
And that failure, that inconsistency, that is your absolute mandate to switch to an agentic workflow,
So instead of throwing a bigger brain at it, you decided to give the brain a structure.
a roadmap.
You realized that this one big complex problem was actually four smaller, distinct, specialized tasks.
That's right. And this is where the solution gets really interesting. Since the biggest LLM couldn't handle it in one go, the team built a multi-step, four-part workflow. And critically, this workflow uses both LLM calls and traditional code, with each step having just one single clean purpose.
Okay, let's walk through these four steps. I think the engineering of each prompt here is really what makes this work.
It is. So, step 1, prompt 1, or P1, is a pure extraction agent. Its only job is to extract. We don't ask it to judge anything or format anything.
Okay, so P1 gets all the raw data, the list of missing items, the big block of notes, and what does it spit out?
It just spits out the items from the missing list along with their matching text from the notes. So for our example, it would produce two clean pairs. Ham, old, and cheese, meh.
Just the two things.
Exactly. And here's the technical detail that makes the whole chain robust. You don't just let P1 output raw text. You constrain it. You use something like a JSON schema or XML tags to force it to deliver a perfectly structured data object.
Ah, so it's machine readable from the get-go.
Precisely. You force it to output, say, a JSON array like item, ham, reason, old. That way, the next step in the chain never has to worry about parsing errors. It's a clean handoff.
That makes a lot of sense. So that structured output from P1 then goes directly into step 2, prompt 2, which you called the classification or validity check agent.
Yes, P2. This is the agent that deals with the P problem. P2 is the judge.
Its only job is to judge.
Its sole purpose is to take that clean input from P1 and categorize the reason as either valid or invalid. And to make sure it doesn't just guess what valid means, we use few-shot learning right inside P2's prompt.
So you give it examples.
Literally, we spell it out.
Mm-hmm.
The prompt says valid reasons include out of stock, damaged produce, shelf empty. Invalid reasons include, forgot, not looking hard enough.
So you're defining the rules of the business for the agent instead of asking a general model to just figure out your company's policy.
You're removing all ambiguity. It uses those examples, and it perfectly isolates that judgment call. So P2 gets cheese, and it outputs cheese, invalid.
Simple as that. Okay, so P2 doesn't worry about comparing lists or formatting, it passes judgment.
Right. Now, here's a really critical distinction, and it's a huge factor in efficiency. Step 3. P3 is a comparison function, but, and this is key in this workflow, it does not need to be an LLM call.
Wait, okay, hold on. The first two steps were LLMs. Why does P3 suddenly switch back to just regular GAID?
Because the task is now purely deterministic. It's simple logic. P3's job is just to compare the list of items that P2 marked invalid against the original complete list of all missing items.
Oh, I see.
It's just a simple set comparison. Is this item in that list? It's something a basic Python script can do instantly and for almost no cost. We only use the specialized LLM agents when we need that human-like judgment, like P2's classification task.
That makes incredible sense, especially from a cost and speed perspective. You're only paying the LLM tax both in time and money when you absolutely have to.
Exactly. P3 runs in a fraction of a second, and it identifies cheese as the only item that was missing and had an invalid explanation because ham got validated by P2.
Perfect. So that leads us to the final step. Step 4, P4, the generation agent.
And this is the easiest job of all because all the hard thinking has already been done.
Right. P4 just gets the short, clean list of problem items from P3, and its only job is to format it correctly.
Yep. It gets cheese as its input, and it just outputs it in the required text file format. Cheese, no explanation. Since its input is so clean and curated, its single job is formatting, which is trivial.
And the whole flow, when you structure it like this,
Yep.
It's robust. It's deterministic.
We move from one confusing single prompt that was failing, maybe 40% of the time on these edge cases, to a four-step sequence that achieved near-perfect accuracy.
The elegance of that structure is it's undeniable. You just looked at the huge, messy task and broke it down to 4 distinct functions: extraction, classification, comparison, and generation.
And that is the core aha moment. That's what saved this project. So why did the biggest, most advanced model fail when we tried to cram all of this into one prompt?
It wasn't because it didn't know about cheese or employee notes.
Not at all. It failed because those competing instructions created a processing bottleneck. When you tell a single model to extract and judge and compare and format, it has to juggle its entire context window and all its internal priorities.
And faced with that ambiguity, meh,
Yeah.
It compromises.
Right. The source material suggests it tries to find a sort of weighted average of compliance. It might sacrifice some logical accuracy on the judgment part just so it can better fulfill the formatting part. It gives you a beautifully formatted but wrong answer.
Which is useless.
Completely. The agentic workflow solves this by forcing clarity. P2 doesn't care how the extraction happened, and P4 couldn't care less about the validity logic. Each agent has one narrow, well-defined job, and that maximizes reliability.
It's the difference between asking one person to run a marathon while also solving a calculus problem.
And asking 4 specialists to each handle one part of the race.
Okay, but let's talk about the elephant in the room here. Latency and cost. Everyone listening is thinking this. If you're making 4 separate calls, 2 to an LLM, 2 to code for every single audit, that has to be slower and more expensive than one big call, doesn't it?
That's a crucial question. And yes, on paper, running 4 sequential steps is technically slower and a bit more expensive per transaction than running one. But you have to look at the total cost. The accuracy moved from, say, a 60% success rate on edge cases up to 99.9%.
So the business context matters.
Immensely. What's the cost of a human having to manually review and fix 40% of your outputs? It's enormous. You're trading a very small increase in runtime for a massive improvement in reliability and a huge savings in human verification time.
This knowledge is just. It's foundational for anyone trying to use LLMs on real-world, messy problems. It teaches you to stop just trying to find a bigger model and start actually structuring the problem for the AI. You turn these chaotic, high-failure tasks into predictable, robust assembly lines.
And it proves that the biggest LLM is often not the right answer. Success comes from breaking the problem into small, manageable steps, and then using the right tool for each step, whether that's a complex classification agent like P2, a simple extraction agent like P1, or just cheap deterministic code like P3. That decomposed sequential approach is the power of the agentic workflow.
So what does this all mean for you, for the complex projects you're working on?
The agentic workflow basically transforms one huge, confusing mega task into a manageable series of specialized missions. You don't just write one prompt and cross your fingers.
No, you deploy a sequence of agents, each one designed to solve one small, crucial part of the puzzle.
The lesson here is that when an LLM struggles with a complex task, it's almost never about a lack of intelligence. It's a lack of clarity in what you're asking it to do.
It's a mandate problem. So the next time you hit that wall, decompose the task. Define the functions you need. Is it extraction, classification, comparison, generation? And then build the workflow to solve the problem step by step. We saw that even for something like a grocery order check, it required 4 highly specialized steps, mixing and matching LLMs and standard code to get it right.
So now think bigger. Take that concept and apply it to a complex process in your work. Maybe it's reviewing quarterly financial reports or synthesizing customer feedback from a dozen different platforms. If you're trying to solve that with one giant prompt right now, how many specialized steps would you actually need? Which parts need that unique LLM judgment, and which parts could be done faster and cheaper with simple deterministic code? What complex process in your world could be totally transformed by shifting from that single monolithic prompt to a sequence of specialized agents? That's the question that really drives innovation.